straight into it. Or, as open source software has over... So R as an open source software has, over the last few years, been exponentially taken up with both academics and especially practice. And what this has allowed us is, it has allowed us easy tools to really interact with complex models and methods. But with this like sort of complex models and methods, what you'd find is that, you know, theoretically they become more complex and mathematically they become more complex. And one thing that I've sort of been striving towards is developing a thought process of, as a practitioner, it's your obligation to take these models and these complex sort of methods and break them down, you know, break down the sort of mathematical hyperbole into insights and actionable things that you can give someone, you know, that they can get excited about. So that's my task for today. And today I want to take a very niche field in statistics called copulas, and copulas are my hobby, and I want to show you how we can use visual inference for these high-dimensional Vine copulas. So for those of you who are not statistically inclined, copulas are very interesting, and it's a problem that we sort of face in statistics a lot, is that you might want to model the sort of joint distribution of two marginal distributions, but one's a gamma and one's a normal, so you can't use sort of a multivariate normal to model these joint distributions. So what you do is you use these copulas, and copulas act as a linking function between these two, you know, differential marginal distributions. And essentially what you're able to do is you're able to compare apples and oranges with each other. So the copulas are applied everywhere, but for me, I like it in financial econometrics. So copulas are very good for dependence modeling, and we use the dependence as correlation. But correlation is unfortunately unaligned to what is the normal distribution, and copulas overcome this in a very brilliant way, so measuring dependence through Kendall's tau. So I'm not going to go too much in that, you read that on your own, but we bridge the sort of dependency. So this is class theorem, and even those mathematically inclined, PhDs in astrophysics and those, this will take you time to figure out what's going on here. So what I'm suggesting is we just visualize this. So imagine that these are my two asset classes, like U on the bottom and V on the side, and this is the density. So we use what is called a normal copula. So this is the marginal distributions aren't normal, the copulas are normal. And we see, okay, in times of sort of, you know, when the market's moving up, these markets move together. When these markets move down, they move down together. And there's a vast array of these copulas. And the beauty of them is something like this. So if your data fits like a Clayton copula, in times of normal market sort of procedure, these assets will be way uncorrelated. So you think your portfolio is nice balanced. But you can see as soon as time of distress sort of enters the market, they cling together, and they will then pull your portfolio down as a joint distribution sort of rapidly declines. So this is amazing that you have these copulas and you can link. But the big problem is that portfolios and transistors and things aren't like bivariate, you know. So the problem that we like sort of run into again is what's called the curse of dimensionality. So what they did was this one sort of researcher, they instead of like going into your d-dimensional space, what they thought of was, but what if we keep it in bivariate space, but we sort of link these things together? And these things are called vines. So let's look at these vines. So I use the Vine Copula package, and this is the output. So essentially what we're looking at is bivariate copula pairs or dependency pairs of the top 40 shares in South Africa. And they're all sort of built out. Now, I don't know if any of you can see what's going on here, but I can't. So my solution is the following. I sort of wrote like a package, and it's a shiny app where you guys can go play, and you can do simple things like 1 year performance or industry. So now we've taken the tree and we made it interactive, and using metadata, we're starting to get inference out of very, very high-dimensional complex objects. And obviously, the obligatory thing is to try and lasso one of them. So you guys can go and play there. And if you want to see my "it just works" sort of code, then you can go press source code. So I think that the conclusion is that as we sort of climb this ladder of complexity and this sort of ease of access in models, it becomes more important. The communication part becomes important in our workflow. And then we can no longer build or keep building these high walls to keep people out. But you're building these walls of complexity. And I think the trick to it all is that if you can successfully convey to someone like why you are excited when you run this model on like a Friday and you come in on a Monday and there's this little number, on your little black Linux terminal, and you're like, this is amazing. So I think if you can find a nice way which has amazing tools and widgets, and there's this sort of vast array of things that we don't always think of because we just press that machine learning model button all the time. And if you can find out to incorporate these things, I find that people will get a lot more excited with you. So if you're interested in learning a bit more about sort of dependence and dependence modeling and Copulas in specific, we have an R Finance. I don't know if you guys know, but we're around. And I'll be hosting a talk there, and the talk will mostly be about how we actually apply these models. And my talk will pretty much handle the application of using Vine Copulas to detect the growing sort of independence among energy markets in multiple stock universes. So yeah, that's it. So yeah, I don't think there's time for questions, but
yeah. Got time for one question.
Okay.